So now we're going to talk a little bit about hypothesis tests. Give a little introduction with an example. So it says the commissioner of the NFL is interested in the body fat percentage of his NFL players. Assume the standard deviation for body fat percentage is 6.22. Now, first of all, we usually don't know the population standard deviation, so we're assuming this value just to illustrate the concept at this point. But so it's not a really real world problem at this point, but it will be. But we'll get to the point where of what we do when we don't know the standard deviation. So from now, we're going to assume that it's 6.22. It says the Safety Council claims the average body fat percentage for NFL players is 8.08. The commissioner feels that it is actually higher. He randomly samples 25 NFL players and finds a mean body fat of 10. Does he find any evidence for its claim? Now, the first thought is yes, he did, because 10 is higher than 8.08. But we have to understand that just because the population mean is 8.08 doesn't mean that we're going to necessarily take a sample of that population and get 8.08. Sometimes we're going to get something higher, sometimes we're going to get something lower. But we actually understand, based on the sample distribution, how these sample means behave. So we'll take a look at the sampling distribution applet again. So I've got this set up where we have a parent population, which is our population. Assume these are our NFL body fats. The mean, notice, is 8.08. Standard deviation 6.22. Now you might be thinking, how do we know that that's what it actually looks like? We don't about the shape of it. Well, we actually don't, and it actually doesn't matter. I'll get into that, but that's based on the central limit theorem. So what we're going to do is, notice I have n equals 25 here. I'm going to simulate. Pretty slow. I'm going to simulate choosing 25 NFL players from this population. They're going to give me one mean. Okay, when they finally get the mean, it's going to put it in this distribution. So this is the mean, one block. That's one animation. In other words, they simulated choosing 25 players' body fats from this population. That's the mean. Well, we talked about this in the sample distribution, so I'll go a little bit quicker here. Let's speed that up. Say, what if we did it 10,000 times? Another 10,000 times. So that's 10,001 reps now. Now, notice that the mean of the sampling distribution, or the sample means, in other words, each time we took a mean, it was one of these blue cubes. Notice that the mean is pretty much the same as the population. We learned that last video. That says the mean of all the x bars is equal to the mean of the population. Also notice that the standard deviation is smaller, and we actually learned a formula for that. It says if we know the population standard deviation, we can divide it by the square root of n, which is the square root of 25. That'll give us the standard deviation of the sampling distribution, which is 1.23. Okay, and lastly, you'll notice that the shape of the distribution is approximately normal. Now, we understood that when we talked about the central limit theorem, it says that as n gets larger, the sampling distribution gets more normal. And we have our cutoff for our class that we're going to use is going to be 30. Anytime we choose a sample size of 30, we're going to understand that our sampling distribution is approximately normal. Now, 25 is as large as this samples will go for this applet. But as you can see, 25 is still under our cutoff value, but the distribution still looks pretty normal, normally distributed. Okay, so, and let me back up for a second. So, I said earlier that it didn't matter what our population is, because as you can see here, the sample distribution is approximately normal. So let's look at another one. Look at the skewed distribution. Now the skewed distribution, this is the default, is mean is 8.08 and the standard deviation is 6.22. So the same as our setup. But if we do a simulation of taking 10,000 sample means Notice that our mean is basically the same as the population mean, and our standard deviation is about the same as it was before, and it actually will be the exact same if we did more simulations. But this is going to become 8.08 the more reps we do, and the standard deviation is going to get basically 6.22 divided by the square root of 25, and whatever that value is, that's the standard deviation. And notice that the shape looks identical to the last, so it really doesn't matter what our population is. Even if we don't know the shape of our population, we do know the shape of the sampling distribution due to the central limit theorem. Okay. So let's back up and see what we have here. We know that the mean of the x bars, the mean of the x bars is equal to the mean of the population. 8.08, 8.08, or 8.09. The more reps we do, the closer it's going to be, but they're the same thing. And we know that the standard deviation of the x bars is equal to standard deviation of the population divided by the square root of n. Okay, so let's remember that our mean is 8.08, I'll call it, and I'll even still. Okay, so it took me 140,000 reps, but eventually the mean became 8.08, and the standard deviation is 1.25, which is, again, 6.22 divided by the square root of 25. So we know that the sampling distribution of x bar, the center is 8.08, and the standard deviation is 1.25, which, again, remember, is 6.22 divided by 5, the square root of 25. And we know our shape is approximately normal. Now, we said that our cutoff value is 30 for our class, and if you look at another textbook, they might use 25, but you look at another one, they might use 40. But you can see, based on that applet, that at 25, it does appear pretty normal. So we're going to get good results here. Okay. So this So what we assume is we have our normal distribution. We know that the shape is approximately normal. And we've assumed that the mean of the population is 8.08. Remember, our population is all NFL players. We're basically assuming that the mean body fat of all those players is 8.08. And we know that each time we take a sample of 25, the mean of that distribution is 8.08 also, and the standard deviation is 1.25. Now, Commissioner got an X bar, a sample mean, of 10. And we can kind of understand what we know about the normal distribution here. If the mean is 8.08, one standard deviation above the mean, if we add 1.25 to the mean, that's 9.33. Well, 10 is going to be a little bit bigger than that right here. And so we can come up with our z-score, because this is what we're trying to come up with. What we're trying to do is say, we're trying to get evidence that the mean is greater than 8.08. So what we do is we say, okay, well, let's assume it was 8.08. How likely would it be, by chance, to get a random sample of 25 NFL players and get a body fat percentage 10 or higher? This 10 or higher would say if that would give us evidence that it's not 8.08. So our z-score, 8.08 minus 10 divided by 1.25. So we're going to use the calculator to get the z-score. We're also going to use the calculator to determine this probability using our normal CDF. Okay, and what we call this probability is a p-value. P-value. Now, the smaller your p-value is, the more evidence you get against your hypothesis here. We didn't get into what a null hypothesis is or anything like that yet, which we will. But what we did was we assumed that the mean was 8.08 until we got evidence that it was actually higher. So the lower your p-value is, in other words, the less likely it is to get a sample mean of 10, the less likely that is, the less likely the mean is really 8.08. So the lower the p-value, the more evidence we get that the mean is actually higher than 8.08. Okay. So now let's go to the calculator. Okay, so we had 10 minus 8.08 divided by 1.25. Now we knew it was going to be between 1 and 2. 1.536 is our z-score. Okay, so we know kind of how probable that is, but we can get a better idea with normal CDF. We're trying to get the probability of getting a z-score higher than that. So let me go to my answer, which is the 1.536. This is my lower bound, because if you think I'm shading to the right, that's my lower bound. My upper bound is E99, which represents for us basically positive infinity. And remember, anytime I'm working with z-scores, I'm going to let my mean be 0 and my standard deviation be 1, which represents the standard normal curve. So if I paste that, I get my p-value to be 0.06. And let's talk about what the p-value means, and I'll leave it there. The p-value says we assumed that the population mean was 8.08. The mean body fat was 8.08. Now, if it really was 8.08, then by chance, we would take a sample of 25 NFL players, get a mean body fat of 10 or higher about 6% of the time. So we'll talk about exactly how probable is 6%. Is that enough to say definitely the mean is not 8.08 if it happens 6% of the time? Or is it enough to say that's pretty strong evidence that it's actually not 8.08 but is actually higher than that? Or is it not enough really to claim that the mean body fat percentage is 8.0 is actually higher than 8.08? But we'll talk about that in another video. But that gives you the concept of really what we're doing in a hypothesis test.